Good afternoon. Section 11.8. Power series. So as you remember, series are infinite sums of numbers. So today we consider a special type of series that look like this. Cn are numbers or constants, which are called the coefficients of the power series. And x is a variable, okay? So we have c0 plus c1x plus c2x squared and so on, okay? So first of all, you notice that this is a function of x, and in fact, partial sums are polynomials. Right? Because they contain different powers of x. Question?
So is the c there the same in each member of the power series, or is it different?
So each coefficient c0, c1, c2 can be a different number. So in fact, we are given an infinite number of those coefficients. Okay. So we can think of this as a function of x. Of x, okay, and of course, in general, it's not really a polynomial because it does have an infinite number of terms. So there is one. The first example comes back to the question just asked: what happens if all Cn were the same? Okay, if all numbers Cn were equal to 1. What would we have? We would have a series that looks like x to the n. And this actually reminds us of the geometric series, right? This is a geometric series with r given by x. So your regular geometric series has some number here. For instance, it has a coefficient a and a number r. This one has a variable x. So for any value of x, this is a geometric series. And in fact, we can say when it converges. It converges if the absolute value of x is less than 1, right? And diverges if the absolute value of x is greater or equal than 1. But this is only a particular type of power series, the simplest one, when all the coefficients Cn are different. In general, there can be all different. And here's an even more general form of a power series. So again, we have coefficients Cn. And instead of x to the n, we have differences x minus a to the power of n. So it's called the power series centered at a. A is a constant. Okay. Now, the main question that we're going to study today, of course, is the convergence of these guys. Okay. And the very important tool is going to be the ratio test. So let's look at the first example. Does the series No, this is the wrong question. Okay, so for what values of n of x, for what values of x the series given by the following n factorial x to the n converges. Oh, one remark, going back. If you noticed, we start our summation with n equals 0, whereas before, when we looked at other types of series, we usually started with 1. This is a convention. When people talk about power series, we start with n. This way, you can see that the first term is actually a constant. And then we'll have the first power of x second, and so on. Okay, in general, this polynomial will contain a constant term. We allow it to be one of the terms. So now we look at this power series. You can see that it's a power series because it's in that form. It's centered around 0, okay? And the coefficients Cn, as you can see, are given by n factorial. So they're all different, okay? So because this contains a factorial, we'll use the ratio test. So we're going to look at n plus 1 over an. So when we do that, we momentarily forget that x is not a constant but a variable. We just fix it to be some value, okay, and investigate convergence. So in this case, an is simply given by n factorial x to the n. So we have n plus 1 factorial x n plus 1 divided by n factorial x to the n. The absolute value goes, and we have n plus 1, and we have x. And what is the limit of this expression as n goes to infinity? Let's write it like this. What does it tend to when for any fixed value of x when n goes to infinity? So there are actually two cases. Okay, if x is not equal to 0, for instance, it's equal to 5, or for instance, it's equal to 0.001, what is the limit here? We have a constant times n plus 1, n goes to infinity, so the limit is, of course, infinity, right? If x is equal to 0, then this term becomes simply 0, okay? And the limit is 0. So we conclude by the ratio test that if x is any number but 0, the power series diverges by the ratio test. If x is equal to 0, the power series converges. So in this interesting example, the convergence is only observed for one single value of x, x equals 0. For any other non-zero value of x, the series diverge. Questions? Okay. So next example. For what x the following thing converges. Okay. So you can see that this is a power series centered at 3, x equals 3. Okay. And we again use the ratio test with an given by simply the general term of this power series, x minus 3 over to the power of n over n. So a n plus 1 divided by a n is x minus 3 n plus 1 n plus 1, and we have x minus 3 to the n over n. Okay, so some things will cancel. For example, I have x minus 3 to the power n plus 1 divided by the same thing to the power n. So I have x minus 3 remaining, and I have n over n plus 1. And I'm going to divide this whole thing by n. So I have x minus 3, 1 plus 1 over n. Okay. So what I'm interested in when applying the ratio test is to calculate the limit of this quantity as n goes to infinity. So the limit as n goes to infinity of this guy is equal to the limit of this expression. What is the limit? And very good. So this goes to 0. So I simply have x minus 3. So now we have to remember the conditions of the ratio test. Do you have a question? Oh, no. Question?
Why did you multiply n?
Oh, I divided numerator and denominator by n to bring it to this form, and it's easier than to argue about the convergence, right? The limit. I multiplied
One step before that.
one step before that. So here, we have the following: x minus 3 to the n, or we can write it like this. Yeah, that's fine. And we have x minus 3, n plus 1, x minus 3 to the n. Agree? I decompose this into x minus 3 to the power of n times another one. These two cancel completely. And what I have left is n is positive, n plus 1 is positive. So I have to take the absolute value of this times n plus 1. Okay. More questions? Okay. So for ratio, so we call this L when we talk about the ratio test. If L is less than 1, we have convergence. L greater than 1, we have divergence. And L equals 1, we actually don't know. Okay? So let's talk about the cases that we do know. If x minus 3 absolute value is less than 1, then the power series converges. Right? So what does this mean in terms of x? You remember what it means in absolute value. It's the distance of x from the number 3. Okay? So if we draw this, if this is 3, x that is closer to 3 than 1 belongs to this. So it's this interval. Okay? So this is the same as to say that x is less than 2 and greater than 2 and less than 4. Okay? So converges. If this guy is greater than 1, then we have divergence. Okay? The only remaining question is, what happens if x minus 3 is equal to 1? Right? This is where the ratio test is powerless. we don't know. We have to kind of check it in a different way. So, and this is usually pretty easy. So we're going to do it by hand. So when x minus 3 is equal to 1, what does it mean? It means that x is either equal to 2 or x equals 4. These are these 2 points. This one and this one, right? The borders of this interval. So let's set, first check x equals 4. Let's first check x equals 4. So we have the series of 4 minus 3, to the n over n. That simplifies very much because it's simply 1 over n. What does this do? That diverges because this is a harmonic series. Diverges. Harmonic series. Okay. The second interesting case is when x is equal to 2. In this case, we have 2 minus 3 to the power of n over n. Okay. So what's 2 minus 3? That's, of course, minus 1 over n. What does this series do? Do you remember this? This is the sister of the harmonic series, but it's alternating. This one converges. Right? So we can write down that here at 4 we have divergence, and here we have convergence. So what's the conclusion? The series converges for x belonging to an asymmetric interval from 2 to 4, not inclusive. And it diverges otherwise. Okay. And this is going to be our usual routine. We use the ratio test or sometimes the root test, and then we check a couple of numbers by hand because those don't belong. They give you 1. The next example, which I like very much, is the following. It's called, the function is called j naught of x, and it looks ugly. Like this. 2 to n factorial squared from 0 to infinity. It's called the Bessel function. Of order. So first that's a j. First we investigate its properties, and then I'll tell you about it, okay? So we're going to use the ratio test to find the values of x for which this function converges. Okay, so an plus 1 over an. So we have minus 1 to n plus 1 x 2 n plus 1 2 2. So everywhere instead of n I put n plus 1 factorial squared, okay, divided by minus 1 to the n x to n 2 to n and factorial squared. So because I'm interested in the absolute value, I can get rid of minus 1s. Okay, I have x to n plus 2 divided by x to n, so I have x squared. Right? I have this. What's this guy? It's n plus 1 n factorial times n plus 1 squared, which is n factorial squared times n plus 1 squared. N factorial cancels, so I have n plus 1 squared. Fine. And I have 2n, and I have 2 to n plus 2, so I have 4. No, I don't need the absolute value, actually. Sorry, this is a square. Okay, so this is, after a lot of simplifications, this is what I get. Question?
Yeah, could you explain the factorial?
So on the bottom, I have n plus 1 factorial, right?
Yeah.
Squared, the whole thing. So n plus 1, can you see here? N plus 1 factorial is the same as n factorial times the next term, n plus 1. Right?
Yeah.
For instance, 5 factorial is equal to 4 factorial times 5. You have to multiply by the next number. And then I square that, and then this guy cancels.
All right, thank you.
You're welcome. More questions? So what I need to know is the limit as n goes to infinity of this expression. So is this difficult to calculate? No. When n goes to infinity, what happens? Goes to 0. And it doesn't matter what x does. Okay, for any x, this guy goes to 0 as a function of n, as n goes to infinity. So this is actually very good. It means that the series converges for any x, okay? For any real x. So when you go back here, this is the definition of this function. You can see it's written as a function of x. This is its name because it's very common in science. It describes many things. It looks like this, but the series is convergent. So actually, this expression makes sense, and it's equal to a finite number for any value of x. So we can plot this as a function of x. And let me plot it for you. So you can, for instance, stick any number of x, for instance, 0.1, 0.2, 1, 2, 3, in your computer and calculate a finite number of terms, like 100, and then you get a very good idea of what this thing does. And for positive x, it looks like this. It looks like a wave of a decaying amplitude. Okay, and here it's symmetric. So this is the Bessel function. Now, I told you that it's a very important function. So actually, to visualize it, imagine a rope hanging from a ceiling, okay? A massive, heavy rope, a long one, okay? And I push it, and what does it start doing? It starts doing this, right? No, that's not good. This is fixed, right? So it kind of, you can envisage what it is. Now, look at this function. Lie on your side, okay? And take a piece of this function, like, for instance, from here to here. So this is exactly the shape of this rope that you will see that it outlines as it dances around. Okay, you can calculate it, you can prove it, you can solve an equation that describes the hanging rope that does it, and the shape is exactly described by this function, only vertically situated. Okay, another application of this function. If you play a drum, okay, no, if you play violin, you have a string, okay, and if you create a note, this string is going to vibrate, which means that it's fixed at this end, and it's going to do this, right? And if you know any string instruments, you know about harmonics. You can put your finger here, and then it's going to do this. Oh, sorry. It's going to do this. It's going to look like this and vibrate like this. Or there's going to be the next harmonic that looks like this, and so on. So these are called harmonics of the sound. A two-dimensional generalization of a violin string is a drum. Okay? It's a circular membrane when you push it, it oscillates in the vertical direction. And the shape is given by the Bessel function. Okay? The shape of different harmonics of that is given by the Bessel function. So if you come to my PDE class, I'll tell you more about it in a couple of years. But for now, we only know about the convergence of this beautiful function. Okay? And the convergence, it converges for any value of x. So let me give you a log of what we have done. Okay? So we have looked at several examples. First, it was x to the n, and convergence was for x less than 1. The next example was n factorial x to the n, and the radius converges only for x equals 0 only. Okay. The next example was x minus 3 to the n over n, and it converged for x between 2 and 4. And finally, we have the Bessel function, 2n, 2 to n factorial squared. And that guy converged for any x, so from minus infinity to infinity. So all these results can be generalized. They are specific examples of one theorem, which we're now going to formulate. So, theorem for a given power series, it looks like this: Cn x minus a to the n. There are only 3 possibilities. So either the series only converges for x given by a, the center, or the series converges for all x, or number 3, the series converges if the distance between x and a is less than r, and diverges if the distance between x and the center is greater than r for some number r positive. Okay? So r, this value r, is called the radius of convergence. And here we can say that r is infinity, right? Because you can think of the whole, number line as the distance between x and a being anything from 0 to infinity. So this is r equals infinity. And here, this formula is set r equals 0. So only at the center does it converge, and nowhere else. Okay? So let us look at our examples that we already covered. Here we can write the value of the radius of convergence. for the first one, the geometric series, the radius of convergence is 1. Okay. The second example is characterized by 0 radius of convergence. It only converges at the center. So you can see that this power series is centered at 0. This is the most general expression. We have x minus a to the n. If we just have x to the n, that's like a equals 0. Okay. So it only converges at a equals 0, at x equals 0. Question?
Yeah, and what is the radius of convergence?
So let me show you an example. So when I'm given a power series like this, it's characterized by a single value a, which is called the center. Okay, for instance, 0. Okay, and this theorem tells you that there can be only 3 cases. Either the series converges when x exactly is equal to this guy, or everywhere, or you can draw an interval. So this distance is r around this guy, and inside this interval the series converges. Outside it diverges, and actually at the moment it's not clear what happens at the borders. So the radius of convergence is the size of this interval. Question?
So then for the third one, the radius of convergence is going to be 1.
Absolutely. Very good. So here you go from 2 to 4. The center was 3, as you remember. So r is 1, right? And for the last one, r is infinity. So very interestingly, this exhausts all the possible cases. For example, we could not have the following picture. The series converges here, and maybe at some point here, and maybe starting from here everywhere else. That's impossible. Okay? The set of x for which it converges can only look like this, or it's equal to a, or it's infinite. That's it. Okay? Nothing interesting like this can happen. And that's good, because it makes it easier to study.
Will there ever be a power series that diverges for all values of x, or will it always converge at some point?
So the power series of this kind has to converge when x is exactly equal to a, because you can see that in this case all the terms are equal to 0. So no matter what, it will converge at x equals a, and this is the minimal case. Okay. Yeah, very good question. Question? Yes?
How do you know that the radius of convergence for the first one is 1?
Oh, this was our first example, and we compared this, or in fact identified this with a geometric series with r equals x. This is a geometric series, and it will converge when r is less than 1 in absolute value. So that's this.
So how do you find the radius of r equals 1?
So you can see that this particular series is centered around 0, okay? And it converges when the absolute value of x is between -1 and 1, which makes r 1. Okay, more questions? Okay, so let me actually draw the general picture. So for any power series, we're going to have a. We're going to have a minus r here, and a plus r here. So everywhere inside here, we have convergence. Everywhere here is divergence. And these 2 points can either be convergent or divergent. Okay. More questions? Okay. So let's look at a couple of examples. So one thing that I forgot to comment on is like this. So when we define the power series, Okay, the enumeration usually starts at 0, although not always. Some of the examples did start with 1. So here, let's look at the first at the very first term. So we have C0 x minus a to the power of 0, right? Plus C1 okay, so I want to attract your attention to this term. So when x is not equal to a, this guy is 1, right? It's some number to the power 1, so this is equal to c naught. What happens to x when x equals a? You have 0 to the power of 0, which is like an indeterminate form almost. So here, when we use this notation to denote the power series, we adopt the convention that even for x equals a, so 0 to the 0 is 1. So as I wrote here, this term is equal to c naught even for x equals a. Although when you set x equals a, it looks like this. We adopt the notation that it's equal to 1. Okay. So now to our examples. So we have a sum from 0 to infinity minus 3 to the n x to the n square root of n plus 1. Okay, so we're going to investigate its convergence. We're going to find the radius of convergence and the set for which the series convergent. So the question is find the radius of convergence and the interval of convergence. What's the difference? Well, the radius of convergence tells me this interval, but it's not clear what the ends do. So it could converge, for instance, between a minus r and a plus r inclusive, or it could be a minus r, a plus r like this, or a minus r, a plus r inclusive, or even a minus r, a plus r, right? So we have 4 possibilities depending on whether this point and this point is convergent. Okay? So that is why the question is formulated like this. We need to find the radius of convergence and the interval of convergence, not exactly the same thing. So we are going to use the ratio test with an given by minus 3 to the n, x to the n, squared of n plus 1. So an plus 1 over an. I'm actually going to ignore the minus sign here because we only need the absolute value. So I have 3n plus 1 x n plus 1 square root of n plus 2. And I have 3 to the n, x to the n, square root of n plus 1. So 3n plus 1 is 3 to the n times 3. 3 to the n cancels, so I have 3. X is here, and I have n plus 1 over n plus 2, like this. So what is the limit as n goes to infinity of 3x times square root of n plus 1, n plus 2, right? This is what I need to calculate. for the ratio test. So this is the limit. So basically, you can do that or just see that the limit of the square root is 1. So I have 3x. Okay, and oh, sorry. When this is less than 1, let's try it like this. So what does it tell me? If 3x is less than 1, then the series converges. So I have to extract the information about the radius. So I'm going to divide by 3. The absolute value of x is less than 1/3, right? How can I rewrite this? I can just draw it, right? The center is at 0. So I have 0. So if the absolute value is between minus 1/3 and plus 1/3, we have convergence. What does it mean? That r, the radius of convergence, is 1/3. Okay, so I answered the first question, which is just to find the radius of convergence. So at this stage, I know that inside this interval it converges, outside it diverges, and I don't know yet what happens at the ends. Okay, so I answered the first question, the radius of convergence. Questions? So to check the ends, I need to check them by hand. So let's take x equals minus 1/3. Okay. After this, I have to rewrite my series. Once I fix x to be a number, this stops being a power series and it just becomes a series. Okay, it doesn't depend on x anymore. So what do I have? From 0 to infinity, minus 3 to the n times x to the n, minus 3 to the n times minus 1/3 to the n, divided by n plus 1. Okay, does it simplify? What's minus 3 to the n divided by minus 1/3 to the n? 1. Okay, so in fact it's n plus 1. So there are two ways to go about this. You can either do some test to compare it with the 1 over square root of n series, or if we write down the terms, when n equals 0, the first term is 1. The second term, when n equals 1, I have 1 over square root of 2, square root of 3, and so on, right? So in fact, this is equal to, starting from 1 of this, okay? And this is a p series with p equals 1/2 less than 1. So it diverges. Okay, so the value minus 1/3 diverges. How about the other one? The second interesting case is x equals 1/3. So I have minus 3 to the n times 1/3 to the n, n plus 1. So this is actually an alternating series. And this is an excellent candidate to use the alternating series test. The terms bn decay for sure, and they go to 0. So this whole thing converges by the alternating series test. So this guy converges. So I'm going to write down the answer to the second question. the interval of convergence is, so which one is included? From minus 1/3 not including to 1/3 inclusive. Okay, so this is an asymmetric interval of convergence here. Questions? Okay, there is one more example. This is the last example. So let's do this. Again, the same question. We have n x plus 2 to the n, 3, n plus 1. Okay, so applying the ratio test, we have n plus 1, x plus 2, n plus 1, 3n plus 2 divided by n, x plus 2 to the n, 3n plus 1. Okay, and this guy simplifies very much. We have 3 at the denominator. We have x plus 2 at the numerator, and we have n plus 1 over n. What's the limit of this guy as n goes to infinity? You can see that this combination of n's goes to 1. So we just have x plus 2 over 3. Okay, so we can say that if x plus 2 over 3 is less than 1, the thing converges. So I need to rewrite this in terms of r, the radius of convergence. So I'm going to multiply by 3. X plus 2 is less than 3. Okay, and I'm going to draw it. Okay, the distance between x and minus 2 has to be less than 3. So I have minus 5, this is 3. And I have minus 1 plus 3 is 1. Okay, so the radius of convergence of this guy is 3. Can you see this? Okay, so when I have an expression like this, it's only one step away from expressing it in terms of r. I just have to manipulate it to make it look like the distance from x, between x and some number is less than something. So this actually is r. Okay. Now we have to check the two ends. Do it very quickly. We still have a couple of minutes. So the questionable points are minus 5 and 1. So x is minus 5. What do I get? N minus 3 to the n, 3 n plus 1. So I can rewrite it like this. So it's a funny looking series whose terms alternate sign and they're multiples of n. So you can see that the absolute value of the terms actually grows as n goes to infinity. And for sure, there's no, they don't decay to 0. Okay, so by divergence test, this series diverges. Okay. The second and last point is x equals 1. So we have to rewrite our series. We have 3 n times 3 to the n divided by 3 n plus 1. Okay. This is because x plus 2, I take x equals 1, so I have 3 to the n. That's this one. So again, this gives me something that looks like this. And obviously, each term, an, they grow. They don't go to 0. Again, diverges by the divergence test. So the interval of convergence is x belonging to from -5 to 1, not including the ends, because on both ends we concluded that it diverges. Thank you very much. Have a happy Thanksgiving. Thank you.